Okay, I'm back, and now we want to continue talking about how stars are born. And we said that normally this cloud of this nebula thing does not want to collapse and turn into a star. So that means that it needs some help. So, what are some ways that we can push on that cloud to get it a little bit smaller so that gravity can act on it? Because the force of gravity, if you recall, was equal to big G, and then it was mass of particle 1 times the mass of particle number 2, and then it was separated by r squared. So that was the formula for the force of gravity. So notice if we could make r smaller, and r is in the denominator, then F would get bigger. So if we can take this cloud and compress it a little bit more, then the R is going to get smaller, gravity is going to get bigger, and then gravity can take over and continue to pull it in and turn it into a star. So what are some ways that we could give a shove to that cloud? Well, one is solar wind. So if you've got a star over here, we know that a star gives off a solar wind. So that solar wind could compress this gas cloud enough that gravity could take over. Okay, the next one is going to be a collision with another cloud. So let's say that this cloud is moving in this direction and this one's moving in that direction, and when they collide, they compress each other. And so that might be enough to get gravity to take over. Okay, another one is an exploding star. So over here, maybe you've got another star that blows up. So when it blows up, that's called a supernova. It sends out a shock wave, and then when that shock wave hits that cloud, it can compress it. And then finally, number 4, at this point, don't worry about it, but it's a density wave. And so our galaxy is a spiral galaxy. It's rotating. And so as our galaxy is rotating, it has these things called arms. And as those arms are rotating around, they push the gas in front of them like a bulldozer. And that compresses the gas, gravity takes over, and that triggers star formation. So don't worry about the density wave thing until we get to unit number 4. All right, so now let's go through the order in which a star forms. So the first thing you got to know is the star fragments. You start with the big gas cloud, and then after a while it breaks apart into smaller gas clouds, which continue to fragment until you end up with a whole bunch of mini gas clouds. Each of those gas clouds is going to become a separate star. Now, I want you to also know this for the exam. As the gas cloud is collapsing, it's heating up. And I want you to know why. So the first one we already talked about. As the R gets smaller, the F gets bigger. Okay, the second one says, since pressure is force divided by area, if the F gets big, the P has to get big. So the pressure of the gas is increasing as it's collapsing. And then the third statement says, since pressure times volume is equal to the number of gas molecules, the Boltzmann constant, and then temperature, as the pressure goes up, the temperature goes up. So the point is, as this cloud is collapsing, it's heating up. So the next thing that's going to do is it turns into a disk. Now, we already studied this. We already did this part here. The disk is going to become the solar system, but we don't care about the solar system. So we're interested in what's happening in the middle of the disk, which is where the star is going to be. Okay, let's take a look at this one here. So as this cloud is collapsing, the R is getting smaller, and it's spinning faster and faster because of angular momentum. So the ice skater, when they bring in their arms, they spin faster and faster. So that this protostar, the thing that's going to turn into the star, is going to begin to spin faster. Another thing we said was it's when electrical materials go around and around, that made magnetism. So as this thing is collapsing, its magnetic field is getting greater and greater. So it has these what's called magnetic jets. So you see magnetism is coming out the top and magnetism is coming out the bottom of it. Well, it doesn't show it in the picture, but we know that a magnetic field comes out and then it goes around and then it comes back in, and then it comes out and then it goes around and it comes back in. So what that picture there is really showing is this magnetic field right here, but it's not showing this part. So what happens is that magnetism starts to interact with the other stuff that's in the disk. And so it gives some of the spinning motion of this thing that's going to become the star to the planets. So the planets begin to spin as a result of that. Okay, then the next thing is the temperature now gets up to 10,000. So if you recall, let's put it over here. So if you recall, the temperature of outer space is like 4 Kelvin, and then the temperature of the cloud initially is, let's say, 30 Kelvin. Okay, as it's collapsing, the temperature is going up. So now the temperature is up to around 10,000 Kelvin. Now it needs to get to 10 million Kelvin before it will ignite. Can you see that? I hope you can. So the temperature needs to get up to about 10 million Kelvin. But it is hot enough that the gases are starting to move around. So at this temperature, the gases are beginning to convect. That's Jupiter. So if you recall, Jupiter has an internal temperature of like 20,000 Kelvin, and we said that the clouds of Jupiter were convecting. And so it's kind of like a star that never ignited. And so we'll talk about that in our next segment. But that's basically what Jupiter looks like on the inside. Okay, then the next thing is it's going to get up to 1.5 million. So now we're up to 1.5 million Kelvin. Okay, and then at that temperature, the heat begins to radiate in the center. And then finally, the temperature gets up to 10 million Kelvin. And at that temperature, hydrogen begins to fuse into helium, and a star is born. And then eventually it levels off at around 15 million Kelvin, which is not that important. So the point is, eventually the temperature reaches the 10 million Kelvin threshold, at which point you then have the thermonuclear explosions. And so now we've got a star. And so if you look at that picture, you'll notice that's the same picture that we had illustrating the inside of the sun. The core, the radiative zone, and then the convective zone. Now this last picture here, though, don't worry about it. So what we have just done is we have shown how the orange star formed, the one that is between 0.5 and 1.5 times the mass of the sun. There are other kinds of stars that look different on the inside, and that would be the little ones, the less than 0.5 solar mass ones, and then the big ones on the other side. Again, don't worry about that. That's not going to be on the exam. So let's take a break, and when we come back, we will go then to our next lesson that you need to know for the Unit 3 exam.